Okay, so today I'm just gonna demonstrate on how to perform image semantic segmentation on images. So it's pretty simple. I'll go through it real quickly. Well, it might take a while, but by the end of this, you should understand how to perform semantic segmentation. So first thing first, let's understand what this is. So here is an example. So what we'll be doing is performing semantic segmentation. So you can think of it as a class, and everything within that class is non-unique, as opposed to where an instance segmentation, yes, you have everything sorted within the same class, person 1, person 2, person 3, and so on, but everything is unique. So you can just think one is unique, non-unique, unique, non-unique, unique. So we'll be doing this basically on a data set that comprises of basically dashboard images from driving, and here it is right here. So I'll put a link to this so you can download the data set. It's pretty easy. Everything's here that you need. So you just need the mask, the images, and stuff like that. So you can see right here we have 5 different classes. You have the car, the road, lane marking, other vehicles on the roads in the background. So I believe they're all right here. You can see them all right here. Road, lane marking, undrivable, movable things, and then your car, your own vehicle. So also here's a description of everything that you need to. So you can go to this link right here. I'll put in the description and download everything that you need. The image is already in here and everything, so you should be good to go. So this is needed. The next thing that's needed is you also need a GPU, because training this on the CPU would take an extremely long time. So you can use Google Colab if your whatever computer you're using it doesn't have a GPU, and just activate the GPU or TPU. Doesn't really matter, but pick one. Also, you don't have to install certain things. So PyTorch is what we'll be using for this primarily. So you won't have to do that. That comes already installed. Comes with Google Colab, so you don't have to install it. But if you don't have that, if you don't have PyTorch installed in your system, you can go to the repository. I'm going to link it below, and all you have to do is clone the repository, and then you could either make replicate the Conda environment, or just do a pip install to install PyTorch, and you should be good to go. So without further explanations, let's get into it. So you'll need 3 files. I'll make the 3 files right now. I'm in an empty directory, as you can see. So you'll need 3 files. You need one to gather everything, put everything together. This is your main file. You need one for your data set, and you need another one for your neural network. So now you have these 3 files: your main.py, network.py, dataset.py. So before I go into it further, let me activate my environment. Again, I'll have like a replicate of this environment. All you have to do is just follow the instructions on the repository, and you should be able to do everything that I'm doing. So let's actually start with the we'll start with the data set. Okay. So what I do is this dataset.py, and we'll start with our imports. We'll need a couple things. So we need a OS, glob, PyTorch, CV2, Torch Vision, and we'll need a dataset from Torch, utils.data. We'll import dataset. So all we're going to do here is create a class, and all this is going to do is just make it easier for us to take that data set that we just downloaded it and involve it into everything else that we're going to do. So we'll call this class, call it seg dataset, and it's going to inherit the dataset class. This is this thing right here. And we need to actually create our variables that we need. So we'll need the directory for the images, not the mask, but the images. We'll need one for the mask, and we also want to make transformations. We'll set that to none. And first thing we do, just define these variables. Now we want everything to be in order, so we'll sort everything so we don't have that problem. And these are PNG files, so all we do is this, and we're good to go. So this is for our images. Let's do the same thing for our mask. So I'll copy that, paste that, blah blah, and let's create one for our mask. All we got to do is do this, change the variable names in the mask directory, and there we go. This is all we need here. Now let's define the length of our data set. Return the length of self.image. Basically, this just finds the folder, sorts it, and then we'll be able to take out images that we need. So let's get those images. Get item self item torch dot is underscore tensor item is equal item dot to list. Okay. Now I usually like to make notes, so I know the sizes of these images are 3 by 164 by 874, and this is a good way to note things just in case you forget. So we'll actually read the image. We'll use CV2 to read those images. So self.image, and we'll get that item at that index, and we'll get the mask at that index too. And we'll grayscale this item. We'll grayscale it. So this is an RGB, this is grayscaled. And then we'll just do this. If we have a transformation, we'll perform our transformation. So first thing we'll do, we need to normalize it. You need to normalize everything here. So let's do that. If you're wondering where these numbers come from, I'm using transfer learning, and usually this is just the standard mean and deviations used for that neural network. Now let's take the image and just normalize it, and for the mask we'll transform the mask, and then we'll squeeze 1. This just adds a 1 to the first axis, so 0th axis. And now we want to create our, basically each pixel needs to represent a class. So we have an image is filled with a bunch of different pixels, a bunch of different colors. We want to make sure that if something's of a certain, pixel range, then we want to assign it a class. So I've already went through this already, and basically this takes a bunch of testing of like printing out the mask and seeing what numbers come out, and then assigning it an integer essentially. So here it is right here. Here are the numbers. So these are the numbers. Oh, my bad. I forgot one thing. If self.transformation. So, oh no, mind, it's already there. So here's the transformation. We'll normalize the image. The reason why we're not doing this at the same time is because of this. We want to make sure those numbers come out correct. So I don't want to normalize the images and do all this at once. So basically these are the numbers. Basically this represents the pixel. So if the pixel is less than 0.25, we'll assign a 4, and then go so on and so forth. And then all we do at this is return the image and the mask. Easy. So that's all you have to do. So now, once this is finished, we're done here. We don't have to come back here. We can close this. Now, let's actually make our neural network. So let's do that. It's real simple. We'll need OS. We need PyTorch. We'll need the neural network. And we need torch vision. Now let's make our class. We'll call it segnet v2. And we'll define our initializers. So, and we'll we need a checkpoint. This is where we're going to save the model. So we'll call this directory models. And the first thing we want to do in here, actually 1 second, do the standard stuff. Self initialize. Now, we'll need a file to say where we want to save this. os.path.join checkpoint directory, and we'll call this segnet v2. You can add a .pt to the end of it, doesn't really matter. Should be fine either way. So what we'll do here is we need to figure out what model we're going to use. So for this, we're going to use a model already provided for us. And if we go here, type in torch vision, not the GitHub. You go here, click this torchvision.models, and we need see, as it says right here, semantic segmentation. So we'll go there. We'll be using DeepLab v3. So you can use either one of these. You'll be fine. Maybe model size will be different, but you can use either one. Already there's classes set out. So this has 21 classes. So we can't really use the this neural network because these are trained on different images. So we need to redefine this. So all we have to do is a couple things. So we just need to take this, we'll call this base model, and from torch vision .models .segmentation .deeplab v3, we'll use this one, and this is going to ask if we want it to pre-train everything, blah blah. We don't want it pre-trained, so we're not doing transfer learning. And then as I said before, the classes that we have in this data set, there's 5 classes, so the classes equal to 5. Like I said, standard, mean, deviation, this is just usually used. You don't have to do this, but it's just standard. So next thing I'm going to do is do a forward pass with this model. So we have defined forward self x, and what we do is just return self.base model x and out, the output. This has 2 outputs. This has an auxiliary output and just a regular output. We want just the regular output. And then if you want to save the model, all you have to do is find self and then torch.save and this state dictionary, and we'll save it to this file. And if you want to load the model, and all you gotta do is this self.load state dictionary and torch.load will load that file. We have an error somewhere. Oh, that's not supposed to be there. This should be shifted down. Okay. So here's everything that we need. We have a file. The model that we'll be using has 5 classes. We're not pre-training it. And then we have a forward pass, and then we have a way to save it and load it. So that's all you need. Now, is a way of like creating. We need to make this models directory, so let's do that now. Let's create that directory. I believe it was models, right? Yes, it was. So now we need to make our main file. So our main file just basically is where we're going to train everything and test everything and display images and so on and so forth. So all you have to do now, just clear everything. So all we have to do now is go into that main file. We'll need a couple things again. We need Torch, PyTorch. Do we need any? I'll just make a couple things. We'll import Torch. We need our data loader. Oh, my bad. From torch.data. We'll import our data loader. We'll have matplotlib and numpy, all those stuff as np import matplotlib.pyplot as plt. We also need everything from what we had before. So from our data set, we need to import our seg. What we call this seg data set. This class is what we need, and we need our neural network. For reference, if these imports aren't working, usually I just take off the dot in the beginning and they should be good to go. We need torch vision, we need transformation, so we'll import torch vision as well. And what else do we need? We need CV2. I believe that may be it. Oh, we also need this. Alright, we need something for our launch function. So import torch.nn as nn. So let's start with our let's just start just referencing everything that we need. So let's start with our main function where we have everything put together. Name underscore equals main. And what we'll do now is put our directory. So for the sake of this, I'll just copy this over. I've already written this. So wherever you save your data set, this is what you're going to need. So go to our repository, download everything, but you'll need a couple things. So you need your images, you need your mask, your mask, and then the way I've done this is I took about 20% of the data set and put this into a validation set. So you can go through the data set, select maybe the first 2,000 images, and then from there you can put that in another folder and you can call them image validation images, and then you do the same thing for the mask and call it validation mask. Now towards the end of this, I did save some of this to an MP4 file. You don't have to do this, but you know, if you want to, you could do that. So let's have some things that let's define some of the things that we need. So we need a device. So we're going to use CUDA. If you do not have CUDA and you're doing this on the CPU, which I said I don't really recommend, you can just do this. There you go. It'll use the CPU if it doesn't find CUDA, but default is CUDA. So let's set our batch size. Again, this is just going to be dependent on your system. You can set it to 32, 16, doesn't really matter, but you can set it to whatever you want. Set the epoch, set that to 20. We have image size. Let's set that to 256. How many workers we want. We'll set that to 4. We'll pin memory. True. And we'll set a seed. And we'll just do the default stuff. Just make sure everything stays consistent. I'll add some other things that usually enhances training. Benchmark. It's true. Okay, so let's involve our pre-processing. So what we'll do is this transforms.compose. All we have to do is transform. So this basically takes in whatever the object is, turns into a tensor, then we'll just resize it. So do that, and then transforms.resize. Image size. So we have a 256 by 256 image. And then from there, we can pre-process everything. We'll do this for the video. We'll use this mainly to like test videos that we want to use or whatever it may be. So we'll do the same thing we had before. Turn it into a tensor. We'll resize the image. And then we'll normalize it again. Okay, and let's create our data set. And we'll set our transform. Is this correct? 1 second. Yeah, okay, we have our imager, our master directory, and then we have our preprocess. Right? And we do the same thing and we just put this in a train loader. And now we do a data loader, pass in our train set, our batch size, how many workers we want. We want to pin memory, and then we want to shuffle this. And then we'll do the same thing for the validation set. It's real simple. If you don't want to go through the work of adding the validation set, you don't have to. Just skip that part that I'm gonna write. But it's a good thing to do. Let's define our model. We'll call it segment v2. And let's have a loss function. We'll be using cross entropy, categorical cross entropy. Our optimizer, we'll be using Atom. Passing the model parameters. Is that the right model? Oops. What did I call the 1 second? I'll save this. I called it segment v2. Let's change this to a capital N. Oops. And change this as well to a capital N. Let's go back to our main file. Yeah, okay. So we're passing the model parameters, and we could set the learning rate to let's set it to about 1 to the -5. Okay. Now we'll have two functions here. So let's start with our train function. And all we're gonna do is pass in the model, the device, the train loader, the validation loader, loss function, the optimizer, and the epochs. So we'll make this function right now. We'll have another one, we'll call it visualize, so you can actually see what's happening. We'll attach in our video directory, model, our video preprocess, and our device. So this is just for after we're done training. So let's actually go and make these functions. So first thing we'll do is make the train function. Okay. So the train function, as I said, it comprises the model. We'll need these things: the model, the device, train loader, validation loader, loss function, optimizer, and the epochs, and if we want to load the model or not. So here's a quick definition of what everything does. It's right in here of all our parameters. Now we'll do this. If we train the model and want to continue it for some reason, all we do is just model.load, and we can load that model and continue training, and then print loaded. Right now, let's set the model to the device. We'll use this for basically tracking our training. This enhances, I guess, the speed of training. So I've used this. You can read up on this. Just go to the documentation and then you understand it a little bit better. So from here it's just standard practices. So for epoch and range of epochs, what we'll do, one more import I forgot. From TQDM, we'll import TQDM. And now all we have to do, put a loop, TQDM, the train loader, and then we'll pass in description, train loader, and then we'll pass in that epoch, and we'll do the same thing for our validation loop. Description, I'll add this F in front of it, and then epoch, and then we need something to track the loss. So from here we have an error, TQDM. Okay, so from here all we do is this, pass in the image, pass in the mask within that data set. And what we'll do, we'll send the image to the device and pass in the data type as well that we want. Do the same thing with the mask. Our data type as well. We'll zero out the gradients. The next thing we'll do is do a forward pass. So make our prediction. We'll get our loss from that. So all we do is loss function, pass in our prediction, pass in our mask, see how far off we are. Do a backward pass. Make a step, and then we'll update. Let's get our total loss. We'll add that. Okay, and then we'll add some training descriptions. And we'll say our loss is equal to loss the item. And then the next, let's save this, make sure there's no errors. And the next thing we want to do is worry about our validation set. So again, you don't need this, but you can make alterations, you can keep things the same. Doesn't really matter. Okay, so let's do that. So we'll do this with torch.noGrad. I'll set our validation loss to 0 every time we reach this iteration, this point. And we'll do the same thing as we did before. I don't really want to copy. We'll just copy everything over. So again, we'll make a for loop. We'll go through the same thing we did here, we'll do right here. So we set our inputs, and then what we'll do, same thing here, make a forward pass. You have a forward pass right here. Also, I forgot to mention, I made a mistake here. This needs to be a long, or else this won't work at all. So this needs to be a long, and also this needs to be a long. And then let's add our losses. And then let's actually set both. Do the same thing we did before. References, loss. And then let's save everything. So we'll say if the validation loss is lower than our best score, we'll set our best score. I've also made another mistake. I've just seen it. I'll fix that in a second. We'll set our best score equal to our validation loss, and then we'll just do model.save. And then you could just add a print statement here, saved. Right here, here's an error. This best score thing needs to be positive, so it's positive infinity. And then from there, you can just do the standard stuff where you could just print out the training loss and the validation loss. Now this is the training function. It's complete. You don't need to add anything else. So here are the parameters and everything. Again, if you don't want to type all this out, I'll have the GitHub repository, and all you'll have to do is just replace these directories with the appropriate ones. So from here, we'll make our next function. We call that visualize, and all we need is a directory, the model that we'll be using, the transformation that we'll be using, and the device. So this basically just takes in that this directory just represents the MP4 file. That's all it does. So if you have some images, or a video of someone driving and his dashboard images, then you could use this on that. And I'll display an example of how this actually works at the end. So a good description of it, I'll type that right in here. Takes the video and turns it into images. So we're just taking those frames of the video. So first thing we need to do is load that model. So that model should have been trained by now. We'll set that model to the device, and then we'll put in eval mode. If you don't want to do that, you can just do torch.noGrad. Same thing as we did before. And then we need that video. So whatever you link to that video, wherever that link to the video is this video directory that we'll be using. We'll be referencing that. We need to get the frame. So let's video.read. We need a counter. This is needed if you wanted to actually we don't need this. But if you wanted to save each frame, there's a way of doing that with CV2. But I'm not going to go into that. So all we'll do is this. So we'll just say while success, meaning we'll do this as long as the video isn't finished. We'll transform that frame at that point in time in that video. So take that image, set it to the device, squeeze 0, prediction equals model dot image, model passing the image, and we need to get the argmax argument, and then you can either do CV2 image show to, you need to turn this into a NumPy tensor again, but you can use CV2 image show and for the image or prediction, and you pass in one of these, doesn't really matter. I believe you might have to make some alterations, but all you have to do is just .detach .cpu. My bad. It's .cpu .detach .numpy. You add this to it, and you can it'll display on the screen. But I'm not going to be doing that here. I'll show you it in another example. So here, all you do is this: success image equals video dot read, and that's all you need to do. Again, I'll just keep this right here. All this won't show the prediction with the mask, but it's a way of doing things. So this is all you need to train the model and basically perform image segmentation. So after you're done, you can run this. So I'll pull up an example right now of what everything looks like. So 1 second as I pull that up. And this example I'm pulling is it's from the same repository. So as soon as you close it, you can use the same thing. So I'll go into it real quick and I'll show you what's happening. I have basically 2 files. It's very similar to the one I had before, where I had 1 second. Let me close this out of this. Oh, 1 second. My print statement. I'll just comment that out for now. Right here, we had our 3 files: our main file, a dataset file, and a network file. This basically is what I've already done, was trained everything, so you don't have to reference any of this. All you have to do is just do a simple line, 2 lines of code, and then you'll have the model for you. It's already trained. I'll have, like I said, I'll have the link in the description of everything of how to run this. It should run smoothly. First things first is you need a file of people driving. So dashboard images. So anything that looks like what we had before, which I'll show you right now. 1 second. Any video that looks like this image should work fine. So I've already trained the models, like I said. You don't have to do anything. You don't have to add any code. All you have to do is this: Python. 1 second. Let me go back. Yeah. So all you have to do is this: Python 3 or Python, what doesn't matter. And we'll use this run.py. We'll call run.py and just pass in this parameter: .load video. And all you have to do, press enter. And what happens is, like I said, I've already trained everything. It'll download the models for you, and it downloads the weights and everything. And then here you go. Now, what we just did is this on the right. And on the left is it's another data set that I've used. You can find it in the same repository. But what we did on the right is basically the example I just did, and the model's trained. And this is what you should get at the end. So that's all. If you have any questions, like I said, just leave a comment, leave a like, subscribe, do all that stuff. Everything is in the repository, so you do not have to write everything again. You can just retrain the model, or you can retrain the model if you want to get better prediction, because you can see this is still, blotchy. You can create, and this is because we trained this on 256 by 256, and we're scaling things up. So you could probably use, if you have a better GPU, you could probably double the image size, and maybe for performance will be better. Well, it should be better. But as you can see right here, everything works pretty well. We have the background, other cars, this car, everything's pretty standard. So you should be good to go. I think that's all I have to say. Just go to the repository, links in the description. It's easy to replicate the environment. It's not that difficult at all. And I wish you good luck.